I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 2 with the course code PHY 313, we are at the lecture number 14 and the topic is Eigenvalues of Angular Momentum Operator. As we know that angular momentum is an important observable in quantum mechanics and whose values are quantized. In order to get those quantized values, we assign an operator to this observable. And then the eigenvalues of this assigned operator are experimentally determinable. In today's lecture, we will see that how eigenvalues of angular momentum operator can be derived. So we start with first the classes of angular momentum. As we know that angular momentum is because of the rotational motion of an object. For example, consider the Earth's motion around the Sun, then there is an orbital angular momentum associated with the motion of Earth or any other planetary object which is revolving in a circle. Similarly, if you consider an example of electron, then when electron revolves around the nucleus, it also has an orbital angular momentum. But there is another class of angular momentum called spin angular momentum, which has no classical analog. So any quantum mechanical object, for example electron, which is of a very small dimension, also has another angular momentum called spin angular momentum. So the first class of angular momentum is orbital angular momentum, usually denoted by L, and as I have given examples, this is a classical property, but we can also have a quantum mechanical orbital angular momentum. On the other hand, we have also a spin angular momentum, and this is a totally quantum mechanical object and property which has no classical analog, and it is usually denoted by the symbol S. Different particles, small particles, subatomic particles, have different kinds of spin angular momentum. For example, electrons' spin angular momentum is 1/2. On the other hand, the spin angular momentum of a photon is 1. So usually we represent the total angular momentum of any particle with the symbol J in quantum mechanics. So this J can be either now L, that is orbital angular momentum. So this J can represent L, orbital angular momentum, when spin angular momentum is 0, or this J can also represent S when we are not considering L, or on the other hand this could be the sum of L plus S. So when in this lecture and usually in courses of quantum mechanics, J is usually referring to the sum of L and S, or we can have a situations where S is 0 and J is only L, or when L is 0 and J is only S. It depends upon the situation. So now this was as far as the notations are concerned, or the physical meanings of the symbol J is concerned. So whenever we will be using J, we would either mean L or S. So in this lecture we will develop a general theory for deriving the eigenvalues of J, and then whenever it is needed according to the situation and problem at hand, one can associate or one can identify J with L or S or some of them. Okay. So next we move to some important commutation relations or properties of the angular momentum J. As you know that in quantum mechanics we have operators which commute or either commute or they do not commute. When there is an uncertainty between certain operators or certain observables, we say that they do not commute, or on the other hand if they commute then there is no uncertainty. So let's check the values of or the commutation relations of total angular momentum J. So we will go by component by component. So the first relation is between the x component of J and the y component of J, and if you see the calculation commutation relation between the x and y components of the J, then this is equal to I h bar J z. So this we have already derived, or you can just simply derive for yourself from the last lecture. This is a kind of revision where we have derived the commutation relations between the angular momentum. And then similarly we can have a commutation relation between the y and z component. So usually the rule is that if you want to calculate the commutation relation between any two components of the angular momentum, then the missing component, this will be equal to the third component, which is not included in the commutation relation. So this is the simple way of remembering this, with a factor of I h bar coming in front. And similarly the third one, and another important thing about the angular momentum is the square of the angular momentum. Remember now that any two components of angular momentum do not commute, that is, their commutation relation is not equal to 0. So all of them is not equal to 0, which means they do not commute and they are uncertain. So as we did in the last lecture, that if the two components of angular momentum do not commute, then we try to find out another property or another value of angular momentum which actually commutes with any component of the angular momentum, and that was j square. So j square is equal to the jx square plus jy square and jz square, and we will see now in this lecture later on that the j square and j, any component of j, will have common eigenvalues, and we will derive them. So once we derive them for any component, the same eigenvalues will also be true for the square of the angular momentum. Okay, this was a kind of reminder from the last lecture, these commutation relations. And the square of the angular momentum and uncertainty principle, as I have already mentioned, that now this j square actually commutes with any of the components. For example, it commutes with the jx, that is equal to 0, it commutes with the jy, and it also commutes with the jz. So it commutes with all components of the angular momentum, but usually we will treat or develop our theory using z component just for the convenience. So by this we mean now that the uncertainty in the x component of the angular momentum and uncertainty in the y component of angular momentum must be equal or greater than h bar square by 2, and this is the jz. So since these two components do not commute, therefore there shall be uncertainty. But on the other hand, if this is the uncertainty in the jx and uncertainty in the j square, then it will be equal to 0 because it commutes. Okay, so now we know that what are the commutation relation between the components of the angular momentum and between any component of and square of the angular momentum. So after having this information, we would like to now in this second part, so I would say this was the first part of the lecture. In the second part, we would like now to construct some machinery to get the eigenvalues of angular momentum and square of the angular momentum. So we need certain kinds of machinery, certain kind of equations which will help us in deriving the commutation, the eigenvalues of j and j square, and we call them ladder operators. So these ladder operators will help us in deriving the eigenvalues of j and j square. So what are the ladder operators? Ladder operators are defined as, for example, let's call one of them as j plus. So this j plus, by definition, we will make it out of jx and jy. So some linear combination of jx and jy will give us j plus. So this is just the definition. So you will see that this will be very helpful while we will derive the eigenvalues of j and j square. So this is the first definition, and the second definition is with minus jx and minus out of jy, and let's also call it j plus dagger. So either this is j minus is equal to j plus dagger, because then we will see that j plus and j plus dagger are associated. So these two are just the ladder operators. If you remember in the first course of quantum mechanics, that we had inhalation and creation operators. You remember that when there was an inhalation operator, it acted on a wave function, and destroyed any particle contained in that wave function. And then we have a creation operator. When it acted on a wave function, then it created certain kind of particle. So these ladder operators are quite similar, that it will take us up in the eigenvalue sequence, which we will construct now, or they will take us down into the eigenvalues equation. So we will see that we will have a sequence of eigenvalues, and moving from one eigenvalue to another eigenvalue will be possible with the help of these ladder operators j plus and j minus. Okay, so once we have now defined this j plus and j minus, so we are in the second part of our lecture. In the first part we just defined the angular momentum, and it's reminded you the commutation relation. In the second part we are developing machinery or the tools for deriving eigenvalues of j and j square. So this was the first of the tools, that is just the definitions of ladder operators. But there are certainly some commutation relations or some other properties between j plus and j minus. So let's talk about them. First of all is that j plus and the commutation relation between j plus and jz is equal to h bar j plus. We will derive this in a moment, but just now note that when j plus commutation relation with jz is equal to h bar j plus, and similarly the j minus when with the jz is commutation relation is calculated, this is equal to minus h bar j minus. Or we can combinedly write them like this, that is j plus j minus jz is equal to plus minus h bar j plus minus. So this is the first property which we have at our hand, and we will use it in order to derive the eigenvalues. The second property is that j plus commutes with the j square. As you can see over here, its commutation relation is equal to 0, and also j minus commutes with the j square. As you can see also here, its commutation relation is equal to 0. And if we write them combinedly, then you see over here that j plus j minus commutation relation with j square is equal to 0. So these two properties are very important properties, and that will be very useful for our derivation of eigenvalues. But it is a good exercise to derive these properties first, to check whether they are really true. So I will derive for you this one of them over here, because there are 4 properties, 1, 2, 3, 4, and I will derive one of them, the first one, and the rest of 3 is just the similar calculations and left as an exercise for you to give you a practice that you check for yourself all these calculations, but the main tools are just similar to the derivation of the first quantity. Okay, let's move towards it and see that how the first commutator comes about. You would already guess that it will not be very difficult. Just to give you the quick version of the calculation, that you know that in this commutation relation there is j plus. So you plug in the value of j plus over here, which will be jx and jy, and then do the commutations. So let's see how it works. So you see over here that in this left side in the commutation relation we have jz and j plus. So how these calculations goes about, that here for j plus you put its value which we have defined, that is jx plus iota jy, and now you know that whenever we have this sort of commutation relation, then jz will commute with the jx. So these are 2 commutators actually. So jz will commute with the jx, and then jz will commute with the jy. So if we write it explicitly, then this is equal to jz commuting with the jx, that is commutation relation of jz with the jx, plus, and this I will go out because it's just a constant. So this will be equal to I, jz and jy. So now we have 2 commutators, jz and jx and jz and jy. And in the beginning, if you remember, we know what are the values of the commutation relation jz and jx, and I given you hint there that whenever some component is missing in the commutation relation, then this commutator is equal to that component. So here zy, so we will get it equal to jy, and this is zy, so we will get it equal to jx. And as you can see over here that this jz jx is equal to I h bar. I h bar is the angular momentum which is going out, so this is equal to jy, and I, since there will be another I, this is equal to I dot I, and jx, and this minus sign comes because this the jy jz is equal to jx, but if the order is inverted, then jz jy will give you the minus sign. That's why you see minus sign over here and this I dot I between them. And do another next step, simple step, by taking common from these two h bar and calculating I dot I is equal to plus, so you get jx plus iota jy, which is the definition of the j plus. Remember that j plus is equal to jx plus iota jy, so we know that now h bar j plus. So you've seen that it was a very simple calculation to calculate the eigen and the commutation relation between jz and j plus, which is equal to h bar j plus. So in similar way, we will be able to calculate all these rest of the three commutation relations. Similarly, you just put the value of j minus over here and do the two commutation relations, and similarly put the value of j plus over here, and since it's j square, so you will be able to calculate j square with jx and jy, and so on with the j minus. So hint for these three calculations, these three commutator is that put the value of j minus over here, do the two commutators and put their values, and similarly j plus for j plus and j minus when they are commuting with the j square. So I have done this first one for you, and these three are left for you as an exercise. Okay, so after deriving these commutation relations and checking that they are really true, the other interesting relations and which we will need for the derivation of the angular momentum are this one, j square is equal to j minus j plus jz square and h bar jz. This is one of the relations. We can also derive this, and this another one, this j square can also be written as, if you invert the order, j plus j minus and jz square and minus h bar jz. You can do this, and the combinedly you can write that this j square is now can be equal to j minus j plus and j plus j minus, so we have combined it written over there, and j square is just the same, and here plus minus is combined here. So this is another very important property which we will use and which will help us in deriving the eigenvalues, is this one. So just note it, and we will also derive one of them, and other one will be an exercise. And the other property is between the commutation relation of j plus and j minus, which is equal to 2h bar jz, and 2j square minus jz square is equal to j plus j minus j plus. You can just calculate, check these, verify these properties by putting the values of j square jz, or from going from the right side, putting the values j plus j minus, and do the calculations. You will arrive at the left hand side. So as I promised that I will derive for you one of them, and then rest are just similar, so you can make the, you can do the calculations easily. So as you know that j square, as I have mentioned here in this first property, is equal to j minus j square is equal to j minus j plus jz square h bar jz. So let's derive this first one, and just to give you the quick version of the calculation, just in your mind, that put the value of j minus and j plus and do the simple calculations, you will get this one. Okay, so what I have done, that to put the value of j minus and j plus. So the next step is very obvious. You just multiply all the components, jx square, jx jy, and jy jx, and jy square. So you get this jx square, jy square, and this jz square, and the mixed components, I is common from them, jx jy minus jy jx plus h bar jz. But as you see that this will this just will go out. If you this is just a commutator, and commutator will give you this go out, and this will be equal to j square, the definition of j square. So in the similar way, you can derive the other relations. I leave it for you as an exercise. So this was the second part of the lecture. So in first part we have just definitions. In the second part we have developed a machinery, noted down important commutation relations which will help us in deriving the eigenvalues of j and j square. So let's now start deriving the eigenvalues of j, and then we will see that since j and any component of j, so we will do it as customary with a jz. So as I already mentioned that the j and any component of j, that for example jz and j square actually commute, therefore they have common eigenvalues. So if we derive for one of them the same eigenvalues, then we have just to prove that the same eigenvalues are true for the j square as well. So we decide to derive it through the jz because it's a little bit simpler. So first we now derive the eigenvalues of jz and then prove that these are the eigenvalues of j square as well. So excuse me, assume that that this is the wave function of any particle, for example electron, and this m is just index showing us the that this is the wave function of the z component of the angular momentum. And by assumption we say that whenever jz acts on the phi m, the eigenvalue is h bar m, because this phi is represented by the eigenvalue of its eigenvalue. So since m is the eigenvalue of the operator jz, so that's why when jz acts on the phi m, it gives us the eigenvalue m, and this h bar is just for the dimensional correction because we will have the angular momentum on both sides. So h bar is the dimension of angular momentum, so we get h bar m phi m. So now we have just assumed that when jz act on the phi m, it gives us the eigen function coming back multiplied with the eigenvalue h bar m. So we have to now show that m is either integer or odd multiple of 1/2. So why we want to show this? Because the eigenvalues, these m eigenvalues, can be either integer, integral multiple, or a half integral multiple, and depending on the particle. So we want to show this, that this m is real in an integer or half integer, and these both cases will give us the spin properties of different particles. Okay, so to do this calculation, let us do the following, that is act on this j plus phi m again with a jz, as you see that either we have jz phi m acting h bar m phi m. So what we do, that we want to calculate the value of jz phi m. So you can think of it that j plus acting on it, but when we make the j plus moving to the right of the jz, so how we can do this? This is equal to h bar j plus j plus jz phi m. So you will be wondering that how it comes about. So let's check it. This is equal to h bar j plus and j plus h bar, just jz is acted on the phi m. Coming from this equation to this equation, you just note that jz acting on phi m as we have assumed on the previous slide, then it gives me the h bar m. So this is equal to j plus h bar m phi m. And in order to show you that how this is possible, you have to go to the commutation relation between jz j plus, because remember, whenever you change the order of any two operators, you have to do it through commutation relations, because commutation relation has both of the orders, that is jz plus j plus is equal to jz j plus minus j plus jz. Now you know, now I have here jz j plus, this one, and I want to change the order. So what I have to do, that take it on the other side and put its value over here, and I will get the order changed. For example, look at here. Now this jz j plus, this one will be equal to this commutation relation, and this j plus jz going on the other side, and then I can act with this jz j plus over here and get the required values. Okay, so this was to show you what jz and j plus is equal to, and this relation comes from, or this relation comes from the commutation relation. So next is the you can check for yourself that whenever because you see that here we have this commutator here, and here this is in ladder operator over here. So these relations are equal to like jz acting on j plus phi m. So since we have one operator which is acting up, so we will get h bar m plus 1 and j plus phi m. So this is kind of you can see that jz is giving us one value up, that is m plus 1, and so from this I got the relationship that whenever j plus acting on phi m, it is making it phi m plus 1. So you remember that we call this j plus as a ladder operator, or an operator. J plus was a kind of operator which was taking us up the ladder. So here you can see that the eigenvalue of phi m is increased by m plus 1. So in this way we can actually construct the whole sequence of the eigenvalues by applying j plus and applying it again. For example, you see in this slide, if we applied it again on the j plus, what we will get that it is equal to phi m plus 1. So as I already mentioned, what we get is the whole sequence. But before that, to show you the sequence, the similar operation can be constructed for the j minus. But since it is an operator which is taking us down the ladder, as you see here, j minus phi m acting on giving us phi m minus 1, this with the help of similar calculation, and this j minus phi m minus 1 is equal to phi m minus 2. So whenever it is acting on phi m, it is taking it one level down, and phi m minus 1, it is taking it further one level down. So with this help of these ladder operators, now we are able to construct the whole sequence of the unnormalized eigenfunctions. So by unnormalized, I mean they are just I mean at the moment we don't care about the normalization. We just want to construct a theory where you can see this whole sequence is constructed. So starting with this in the middle phi m, you can see with the ladder operator, for example j plus, you move up here and you get phi m plus 1, the first up value, and the second, and so on you go. And with a j minus, you go here and you reduce the values with a m minus 1 and m minus 2 and so on. So this whole sequence of unnormalized wave functions is constructed, and you can move around in it with the help of ladder operators. So in this third part, first thing which we have done is to use the ladder operators to construct the whole sequence of eigen functions, and we can move in these eigen functions with the help of our these two ladder operators, j plus taking us up the ladder and j minus taking us down the ladder. And now the next thing we have to prove is just that these eigen functions are separated in a unit step. These are separated by unit step, and then at the end we will see that this m corresponds to either integer or half integer, will give us the spins of all kind of particles. Okay, so now we move first of we have this sequence constructed, and in the beginning of the second section of the lecture I told you that j any component of j, that is jz square for example, commutes with the j square. So once we have the eigenvalues for the jz, we will have the eigenvalues for the j square. The only thing which we have to prove now that these values are also true for the j square. We don't have to derive them again, but we have to prove that they are true for the j square. So since jz and j square commute, therefore they have common eigenfunctions, common eigenfunctions. So let's say that j square when acting on phi m have the eigenvalues h bar k square phi m, okay, and where k is a wave vector. And operating with j plus, what we get if we operate with the j plus on this one, j plus with the j square. So since this j square acted already, so we will have h bar k square and the j plus then acting on phi m, and then you can write this h bar k square as equal to j square. So what we have done, that since we know that j square j plus commute with each other, so you can just change the order without doing anything, without adding any term, because they just commute with each other. Okay, so using this relation, that is j plus acting on phi m is equal to phi m plus 1, now we see that it is also the eigenfunction of j square, because as here, when j square acting on j plus phi m and j plus phi m is equal to phi m plus 1, so that means that phi m plus 1 is also the eigenvalue of j square. So once proving that the eigenvalues of z are also the eigenvalues of j square, now we move towards having these conditions. Because of the values of the m, we will have certain kind of conditions on the eigenvalues, and these conditions are on the eigenvalues of total angular momentum are, for example, j square is equal to jx square, jy square, the expectation values. We are just talking about the eigenvalues, so therefore we will have expectation values, and these are equal to h bar k square. And so that means that h bar k square, and we know the values for the jz, that is equal to h bar square m square. We don't know about jx and jy, but we know these two values, and from these two values we will be able to construct the conditions, and average values are then h bar k square, or the expectation values are greater than or equal to h bar square m. So we know that this h bar k square is equal to the this full thing. So it means that there is something which is added to h bar square m. So this must be greater than h bar square, because there is something some addition coming from this part. So therefore this h bar capital K square must be greater than h bar small m square. So these are the conditions we have just constructed, just developed from the definition of j square. And now we know that the absolute value of k must be greater than or equal to m. So it means that m is related to k in some sense, and in this is the sense where we say that when for any positive k, the possible values of m are between plus k and minus k, that it will range from positive k to the minus k. So for any value of k, for example, if k is equal to 2, then we will have the value of m going from plus 2 to minus 2, so on. So maximum and minimum values of then, since if we take the maximum value of m, that is, and the wave function, corresponding wave function is phi mx, then by definition says this is the ladder operator which is taking us up the ladder, but when then the ladder finishes, then there is nothing to move higher. Therefore the j plus acting on the phi maximum by definition is equal to 0, because there is nothing left to move up further. Therefore when j plus acting on phi maximum will give us the value equal to 0. And similarly, since we know that phi minimum is the lowest value and j minus is actually taking as the lower and lower, but lower than phi minimum is not possible, therefore j minus is equal to 0. These are the two very important relations, that is j plus acting on phi maximum equal to 0 and j minus acting on phi minimum is equal to 0. Remember that this is because of the ladder operator construction. So now you know that how ladder operators are helping us to derive the conditions on eigenvalues, because we know that these are ladder operators, these are taking us one value up in the sequence, so at the maximum value they must be equal to 0, and similarly on the minimum value the j minus must be equal to 0. Okay, so now from these relations we know that remember that this we defined at the beginning, that j square is equal to j minus j plus and j plus j minus jz square h bar jz, and we obtain this one. You just put in the value of j minus and j plus and you will get this one. This is not a difficult calculation, that when j square acting on the phi maximum, this will be equal to h bar k square phi maximum, but this is equal to jz square plus h bar jz. So this is just putting the values of these, and you will readily derive. And so now we know that h bar k square is equal to h bar square m maximum into m maximum plus 1 because of the j plus structure, and similarly is the condition for the j square acting on phi minimum. This will be equal to h bar k square phi minimum, but then this is equal to jz square phi minimum, but just the sign opposite. In the maximum case it was here plus sign, and in the minimum case here it is minus sign, otherwise rest is the same. So now we know that h bar k square is equal to h bar square m minimum minus 1. And since in these two equations you see the h bar k square equal to this whole thing, and then h bar k square is equal to this whole thing, this can only be true if it shows us that if m maximum is equal to m maximum plus 1 and m minimum. So this can only be true if and only if m maximum is equal to m minimum. So this is only satisfied if we have this condition satisfied. So this gives us the possible values of m now, and possible values are, if we call this m maximum, is by definition is equal to j, and j is an integer, which means it has values 1, 2 and 3. Then if m is 0 is included in the sequence of m, and j is an half integer, that is it is multiplied by within 1 or 2 with an odd integer, if m is not included in the sequence. Because if 0 is included in the sequence, then how this j or the ladder operator will work? This is increasing it by one step. So if one step is increased, so this must be equal to integer. And if it is if 0 is included, and if 0 is not included, then it is in half integer. In order to clarify this, I give you over here. So in either case, this one or this one, this equation is anyway true. But in order to give you the clear understanding of this concept, I give you the schematic diagram. And in this schematic diagram, consider that this is the m maximum value, and it ranges from plus k to minus k. And when you come one level down, so you will get the value over here. This is phi maximum minus 1, phi maximum minus 1, and then the if you go down further, you will get m is equal to 0 in the middle, and if you go down further, you will get m minimum plus 1 and m minimum. So you see that the whole thing is in the steps, in the unit steps, going from phi maximum to phi maximum minus 1 and m0, m minimum plus 1 and m minus 1. So these are going all going from steps of unit steps, going from unit steps going from m maximum down, we going downstairs in the unit steps, so going from plus k to the minus k. So in this schematic diagram, you can see that this ladder operator actually works between m maximum and m minimum, and when m is equal to 0 included, then we will have this this is equal to integer, this j is an integer, otherwise this is half integer. So this is an example where you see that when j is equal to 2, we have m is equal to 2 m1 and m0 is included. And let me also give you an example of j is equal to 3 by 2. When m is when 0 is not included, you see that it is in half integer example. So this gives me the spin integer spin example, and this gives me the spin half integer example. Okay, to summarize what we have learned today, first of all, we now know that j square eigenvalues are this in terms of the j plus, and jz is equal to h bar m j, and mj ranges from minus j to plus j. And these were the other commutation relations or other properties of action of jz when it is identified with the only orbital angular momentum and spin is equal to 0. So these were the equations, and these were the ranges which we have derived. And finally, when the maximum and minimum values are equal, that is both are LL, then L plus will annihilate this kind of, and L minus will also annihilate this, because these are the maximum and minimum values. So in today's lecture, we have talked about in detail for deriving the eigenvalues of angular momentum. And we know that j and j square commute, therefore they will have common eigenvalues. And we have first derived the machinery. In the first part of the lecture, we have made some certain definitions of the commutation relations. In the second part, we have derived the machinery of ladder operators in order to help us construct the eigenvalues of j and j square. And then in the third part, we went on for constructing the eigenvalues of j, and then similarly we shown that these are the common eigenvalues of j square. and then it gave us some conditions on the eigenvalues which helped us deriving the full sequence of these eigenfunctions of the ladder operators. And once we had this full sequence, now we know this how the eigenvalues of the j and j square are constructed, and they are two kinds of two kinds, half integer and full integer, and how they are related. So I hope you learned, and I have given a few exercises and assignments in this lecture. I hope you will be able to do this. With this, I thank you all.